Hello, good morning, students. So this is the ninth lecture in control systems. So today is 3rd of May 2021. So in the lockdown period, we are starting with the module 2 today. So far we have completed the module 1. 8 lectures have been given to that. Yes, but some numericals on electrical and mechanical system modeling that have to be done. So we will do that on this week Saturday from 3 to 5. So it is on 8th of May from 3 to 5 we will be doing that numerical session. Plus many numericals I will solve and upload, and a lot of numericals will be given to you as your homework. So some 15 to 18 numericals I have shortlisted. All those numericals on electrical and mechanical system modeling, that is RLC and MBK, FB, FI, TV, TI model, all those things we have to solve on module 1. So I'm starting with module 2, and module 2 is actually the transfer function finding technique for given system for by using block reduction technique as well as by signal flow graph. Now, any of the methods we use, we shall be able to find what is the transfer function of the system. Now, whenever we are finding transfer function of the system, from there, whatever is the denominator equation, that is denominator equation in S, that equal to 0. So that is the system characteristic equation. So from given system to transfer function, denominator equation equal to 0, characteristic equation. Now if we solve the characteristic equation, whatever roots of the characteristic equation we find, we check what is the real part of it. So not necessary that every time the characteristic equation will be having real roots. Sometimes it might be having imaginary root. So if it is real root, no problem. We have to check whether the roots are positive or negative. If the real roots are all negative, that means all the roots lie in the left hand side of S-plane, system is going to be called as stable. Which system? Whose transfer function we have found. If the roots are imaginary, that means a plus jb, a minus jb, or minus a plus jb minus a minus jb form. So if the roots are imaginary, then you have to check what is the real part of that imaginary root. So the imaginary root is having both parts, real part as well as imaginary part, a plus ib kind of a thing. So that real part of imaginary root should be negative. That means we can say that in that case, the roots are lying in the left hand side of his plane. In that case, the system whose roots we have found is going to be called as a stable system. Now, if roots lie in the left hand side of S-plane, system is stable. Between that, a lot of things are there and can be explained. Okay, that is not directly written in the book, but in due time, during lab, during lecture session, we will see why it is called that roots are in the left hand side means system is stable, and roots are in the right side means system is unstable. Why so? So that understanding we have to develop. So why are we doing this two techniques? That is the first two parts of block reduction technique and signal flow graph. So in exam, at least in two questions of 20 marks each, that means total 40 marks of questions will be asked from control system in module 2. So in that, at least 30 to 35 marks you can expect it will be asked from block reduction technique and signal flow graph. So you cannot leave any of the techniques. So both the techniques you have to prepare thoroughly, and both the techniques are actually helping us to get what is the transfer function of the system. And if we can find transfer function of the system, from there we find a characteristic equation. From characteristic equation we find what are the position of the roots of this characteristic equation, and we have to see whether the roots are lying in the left hand side or right hand side. If a system is having 10 roots, or if a system is having 10 different state variables, so it's a 10th order system, then we'll be finding there are 10 roots. Okay, 9 roots are in the left hand side of S plane and 1 root in the right hand side of the S plane. Then also the system will be unstable. So even if one root lies in the right side of S plane, S-plane, that is right side of j omega axis, then also the system will be called as a unstable system. Why so? Mathematically we will see. So for that we will have to know what is actually the stable system and unstable system characteristics. So all these things we will discuss in due time, maybe third, maybe fourth chapter. But here, first job, we are supposed to find out transfer function by using block reduction technique. So there are a lot of rules that we are going to discuss today, and signal flow graph. So in signal flow graph, one unique thing is there. It looks a little difficult in initial stage, but as we keep on practicing, you can write down the transfer function of a very big system in one line. Okay, so that is, I will show you how to do that, but definitely in exam you cannot do that. You have to show all the intermediate steps. You have to show how the signal flow graph for any given block diagram is produced, and step by step you have to go 2-3 pages of calculation, showing and all, and finally you have to show what is the transfer function by SFG or signal flow graph. But if you are in hurry, if you just want to show me or in the class, or maybe a system is given to you, you just want to find out what is the transfer function in one shot, in one line, or maybe in 2-3 steps, you can find out what is the transfer function of the given system. So what we are going to do today is the starting part or the introduction of block reduction technique. That means given any system, so the system can be electrical, mechanical, it can be hydraulic, temperature based, pneumatic, okay, it can be a robotic arm, it can be a satellite. So any system given to you, we should be able to find out. So if it's a continuous time system, obviously we shall be able to find out its transfer function in Laplace domain. That is ys by xs, or sometimes it is called as cs by rs, or it is called as ts, capital T, and it's found in s domain. So systems are given in continuous time domain. It's a differential equation. We have seen in the first chapter that LRC system current voltage differential equation is given. We take Laplace transform in both the sides, then we find output parameter divided by input parameter both in s, and then we find some transfer function in terms of some polynomial. So the same kind of thing we are going to do here, but in this case, instead of those systems, we will represent the systems in block form. What is a block? We have seen what is a closed loop system. So in the so there is a forward path, there is a feedback path. So in the forward path there is controller, in the forward path there is actuator, the plant itself. So all of them might be having some transfer function G1s, G2s, G3s, and in the feedback path there is a sensor, and there might be a feedback amplifier, so they might be having a transfer function of GHS. So forward gain is called as G, the reverse gain is called as H. Then we will see what will be the transfer function of the overall closed loop control system. Okay, so there is something called as open loop transfer function, there is something called as closed loop transfer function. So if the system is having feedback, it can be positive type, negative type. So if positive feedback, then what is the transfer function? If negative feedback, then what is the transfer function? If it is open loop system, then how to find transfer function? And from transfer function we can find out the poles, characteristic equation. From poles we can find out stability. So this is more or less the introduction for module 2. You can find here, this is the syllabus given. So transfer function determined from block diagram, block reduction technique. Then there is a formula which is called as Mason's gain formula. We use that Mason's gain formula and we find out the transfer function of the system by using signal flow graph. So signal flow graph actually uses the formula which is called as Mason's gain formula. And whatever system we have seen previously in the previous chapter, so some more numericals we are going to solve. So whatever systems are given, we can find transfer function for that. But what transfer function is actually going to give us? So we can give certain kind of input, we can find out how much will be the output. That is the first thing. Second thing, for different kinds of input, so actually we are finding ys by xs is equal to some transfer function. Now ys is equal to xs into that transfer function. Now if I'm giving unit step input, xs is equal to 1 by s, because 1 by s is the Laplace transform of ut. So if I'm giving the input to the system as ut, then ys, that is the system output, will be xs, that is 1 by s multiplied by transfer function polynomial. So if we take inverse Laplace transform, then we can find yt. Same thing if we are giving input as, instead of unit step, if we are giving input as delta t, Laplace transform of which is delta s. Okay, so if we want to find out what is the system response with impulse given as the input, so we can find out ys is equal to delta s into the transfer function ratio polynomial. From there, if we take inverse Laplace, we can find out what is yt is equal to. So what is the significance of transfer function? First thing, we can find out characteristic equation. We can find out what are the pole positions. From pole position, we can find out the system stability. That is the first thing. Second thing, ys by xs is given for different types of inputs. That is, xs can be sometimes a ramp, sometimes it can be unit step, sometimes it can be impulse, certain time it can be sinusoidal as well. So xs is what? It is not mentioned in transfer function. That depends on us. So ys by xs is equal to ratio of polynomial. Ys is equal to xs into ratio of polynomial. Then if you take the inverse Laplace, yt is equal to the whole inverse. So you can find out output in time domain for any kind of input signal. So this is a very big statement. That is, by transfer function we find ys by xs, and ys is equal to xs into the transfer function. Then xs can be anything. So xs can be found for any kind of input signal. From there we can find out ys. If we take inverse Laplace, we can find out yt. So for any kind of input signal, if we know the Laplace, if we know the transfer function, for any kind of given input signal, we can find out what is the output in time domain. So yt can be calculated from transfer function. So these are the significance, these are the uses of transfer function. And finally, after signal flow graph and Messersgan formula or block reduction technique, so these are the mainly two topics. There is block reduction technique is the first topic. We will solve some 10-15 numericals on that. Then the same numericals can be solved by Mason's-Gain formula, signal flow graph. So this is the main chunk of work in the second module for us. And finally, we will see characteristic equation, how to find it. We know denominator equation is equal to 0 is the characteristic equation. Pole 0 position determination. So find the roots of numerator polynomial and denominator polynomial. So they are going to be the position of poles and zeros, and from there we can define what is the stability of the system in S domain from the pole position. So all these things we are going to do in this module. So out of 40 you can expect 32 to 35 marks from first two topics, transfer function and Mason's-Gain formula. Mostly they are numerical only, so theory is not asked. And from the last topic you can expect 4 to 5 marks of question. That is there. There are case studies. So there is a disk drive. So hard disk drive, we know, we all have used, but we don't know exactly how does that thing function. So we are going to model of that. So first we are going to find out the transfer function based model, and we can find out that disk drive transfer function based model. We can find out its transfer function. And in self-learning topic, so there is something called as impulse response and step response for transfer functions evaluated by block reduction. So whatever xs, ys by xs we have found, transfer functions we have found, we have to take xs as delta s. That is impulse signal when we are giving, we have to find out what is ys. So ys is equal to delta s into ts. From there find yt. So when impulse signal is given to the system, whatever is the system output, that is called as impulse response of the system. Whenever step signal is given to the system, so step signal is ut, Laplace transform is 1 by s. Whenever step signal is given at the input to the system, then whatever is the output that we are obtaining from the same system is called as step response. So after finding transfer function, we can find out what is the impulse response and what is the step response of the given system. So those are self-learning topic. But while solving the numericals, a few numericals, we will see on impulse response as well as step response. And step response is actually the time domain response of any system that you have seen already in network analysis. So all these things we will have a relook into. So what I'm starting with today is, so today is the ninth session, ninth lecture in the first session of the module 2. So here we are going to start with the theory of block diagram by using transfer function based method. So I'm taking you to the next slide. I'm giving you 1 minute time. Just go through what is written here. So the same thing you can find out in our textbook which we have mentioned, that is M Gopal. It is page number 104. Okay, so the book PDF is given to you. In that book of M Gopal, page number 104, the same theory you will find. So I'm giving you 1 minute, just go through. I will explain each and every part of it when I come back. So just give me 1 minute and you just go through these topics, whatever is written. Okay, I guess you have read this thing, so some of the things you might not understand. So let me explain what is given to you. So this is the basics of transfer function based modeling. And here, let us see what is written. So control engineering or control system engineering is an exciting and challenging field within the engineering science because its very nature is multidisciplinary. So I told you in the first lecture, that is, you go from economics to medical science to rocket science to electrical, electronics, mechanical, civil, automobile, any field. Okay, so share market, you can check epidemic control, birth control in a country. So ship control, cruise control, anywhere you go. So there is not a single industry, there is not a single entity where control system is not there. So multidisciplinary is the basic nature, and it plays a critical role in many practical technical applications. So how to control an epidemic? What are the parameters or what are the variables that is causing this epidemic? How to curb it down? How to make the curve flat? So all these things fall in the control system domain. So to be more specific, control theory brings together such different fields as electrical, mechanical, chemical, applied mathematics, you can say, then share market, finance, business, hydraulics, pneumatics, medical science, everything. Okay, finance, economics also. So it plays a major role in engineering applications of all kinds of complexity. This may be a DC motor, robotic arm, aircraft, satellite, power plant, or plant for chemical industries such as a distillation column. So all this system modeling is possible and control by using control systems. So the most fundamental idea for control theory is to change the dynamical behavior of a plant. So I told you that first there is the error signal. Error signal goes to the controller. Controller is the brain of the system, and controller actually generates output which goes to the actuator, and actuator actually gives the signal to the plant so that the plant behaves properly. Okay, so if the plant is under heavy kind of disturbances, if the plant output deviates, then we take the output from the output of the system by feedback. We take it to the input to the controller, and we try to control the parameter, and we try to keep it within the control limit. So whatever is the range of the output, we want to keep it in that range, so pre-decided range. So the most fundamental idea of control theory is to change the dynamical behavior of the plant, provided it is not behaving properly. It is behaving properly, no problem. But the plant is under disturbance, it is not behaving properly, then comes the good or big act of the controller. So such that the dynamics gets a certain desired properties. So if it is already within the certain desired properties, there is a plant output, we don't mind doing anything. So my parents want me to score a first class in every exam, so I am scoring first class in every exam. My parents are happy, so no control. But sometimes if I don't study, if I get second class, third class, or if I fail, then my parents might give up correction to me कि बच्चा पढ़ लो, you are not doing it right, all those kind of thing. Okay, so in almost all cases the controller design is done by building a mathematical model. So first we try to find out what is the input output relationship. Okay, so that we do by a mathematical model, and easiest mathematical model is transfer function based model. So this mathematical model, which can be emulated on a computer and serves as the basis for controller synthesis. So if we know the process well, the whole process, the plant, okay, the input output relationship of the plant, then only it is possible to control the parameter. So sometimes we cannot make a few students pass because we are not deeply involved with him. So first I have to know the students very well, the students who are failing in some subjects. So to make him pass, first I have to see where he is at present, what kind of level he is at present. If I know that, then I can give corrective signal accordingly and he will pass. But if I don't know my process as a controller, then it is very difficult to control that process. So first job in any control system to build a mathematical model which can be emulated on a computer and serves as a basis for controller synthesis. So first we know the process, and when we know the process dynamics, accordingly we can design the controller. There are many types of controllers: analog, digital, feed forward, feedback, open loop, closed loop, and there are many. Adaptive controller, modern controller, many types of controllers are there, and not all controllers are used for all processes. So depending on the process dynamics, there are certain types of controllers. So it is very necessary to know the process, and then only we can say that yes, this controller is best suitable for controlling this process. So it is obvious that the model represents the real system only to a certain degree of accuracy. So there is always an error in the modeling because model might not capture some system dynamics. So the system model can be 80%, 90% correct, but a lot of times there is the amount of error is more. Like today somebody saying whatever pandemic is going on, you have seen last year, and whatever pandemic is going on by June 1st, this will be all taken care of. So that was by mathematical model. But what we found was in the month of July, August, and all, the huge peak had come. Okay, and whatever mathematical modeling was done for this pandemic, nobody has expected the second wave to come. Okay, that means whatever dynamics the virus was having, lot of hidden dynamics was there that we could not capture in our model, and that actually generates some kind of error. So that's why it is saying that it is obvious that model represents the real system only to a certain degree of accuracy. Now our job is to increase this accuracy to 80, 90, 95%. Okay, it should not be a 50% correct model. That is very poor. Okay, so despite this, the controller has to work for the real system as well as for the model. In other words, it has to be robust against errors in the mathematical model. So the controller should be a robust controller. Robust controller means actual meaning of robust in control system is multi-input, multi-output. But here, whatever robust they have meant is any kind of changes comes in the controller, any kind of disturbance that comes to the plant, but the controller should be able to tackle it, and controller should be able to produce output within a certain required band. Okay, so that is what they have meant by robust against errors in the mathematical model. So that is the job of the controller, that any kind of error might come, any kind of deviation might happen to the controller output, or sorry, the plant output. But when that is fed back, the controller should be able to correct it, and within 2-3 control loops, the controller should be able to bring the output to a pre-desired value. That is what they have meant by robust controller against any kind of disturbance or error. So building a mathematical model for a plant actuator or sensor means that physical laws have to be applied to find the differential equations which govern the system dynamics. So these are all continuous time system, and they are all can be governed by a set of equations that is called as differential equation or ordinary differential equation. That is nothing but variable with respect to time. How the variable is changing with respect to time, whether it is the second order dynamics or third order dynamics. Third order dynamics means d cube xt dt2. Second order dynamics is d2 yt dt2. So all those things we have to find out. So whatever plant, actuator, sensor, all these things are there. They are related to some kind of physical law. Sometimes it can be temperature, sometimes it can be pressure, sometimes it can be both. Okay, so we should be able to represent any system with a set of ordinary differential equation, and then take the Laplace transform, segregate into both the sides, then find what is output by input, that is the transfer function. So whenever we find transfer function of the system, analysis becomes easy, because from the transfer function we can find out what is the denominator equation, what is the pole position. As soon as we find what is the position of the poles, at that time controlling the system becomes easier. So what they're saying is building a mathematical model for a plant, actuator, or sensor means that the physical laws have to be applied to find the differential equations which govern the dynamics of the system. How many energy storing element is there in the system, we have to know, because they are causing the bigger dynamics. Okay, so capacitor and inductor you found in case of RLC circuit, okay, they are changing in a different manner, okay, and their property is different. So which are the energy storing element, how many energy storing elements are there in the system, all this thing comes to us very easily if we are able to find out what is called as the system model. So a decision has to be made on the level of detail to which the mathematical model has to be developed. So if you want very highly accurate model, then you have to make a mathematical model with many number of variables. So input output relationship can be represented roughly or very accurately. So roughly means you are mainly capturing the dynamics which are causing major changes in the system. Okay, but there can be dynamics which are causing very less changes in the system, but still they are there. Okay, likewise. So a decision has to be made on the level of detail. So whether you want to take all possible variables and their dynamics, or you are going to take mainly some 4 5 major variables and generate the system model with some kind of error. Okay, so it depends on the accuracy that you want from the model. So decisions are to be made on what level of detailing or what level of accuracy you are expecting from that model. So if you want more accuracy, many number of variables have to be taken. So your observation or experiment set to find out the model has to be more rigorous. So this requires good engineering judgment and some experience. So this is actually called a art of engineering. That is development of mathematical model for any system. So this is actually the art of engineering. This is not a science because there is no direct rule as such. Okay, so which parameters are affecting the input-output relationship, that you have to understand by the whole understanding of the system that is there. So once the differential equations which govern the system are found, a computer simulation is built for analysis. And this may be done by using simulation tools such as MATLAB, Simulink. So Simulink is a very good tool. Many of you have already done the on-ramp Simulink course and submitted the certificate. And then ekdam below of that same page, you'll be finding that on simulation and modeling also, MATLAB is offering a course. So in due time, in this semester only, we have to attack that. Okay. So if you are done with MATLAB and if you are done with Simulink, then towards the end of that MATLAB course page, you'll be finding a one course they're offering on system modeling. So if you can do that and if you can submit that certificate, that will be very great. Or wait for me, when I get more certificates from my students. Almost all the students of A division are done with MATLAB and Simulink on ramp. Then we can attack that mathematical modeling course. So in this semester only, we have to finish that. So there is no simple recipe for model building which is applicable to any thinkable situation. So same modeling technique applicable to all systems, not possible, because every system behaves differently. Every system dynamics or differential equation is produced in a different way. Every system input output relationship, number of variables, all these things might be different. So it is more than science. I told you, it's an art. So how to develop that model? We should read quite a lot. We should see many types of models. Then we will start understanding how can a model be developed. So this transfer function based modeling is also one way of finding the system model, and there's a very easy kind of system model. And we have found out whatever are the advantages and disadvantages or limitations of transfer function based system modeling. So in transfer function based system modeling, first thing, biggest difference is we are considering all the input conditions or all the initial conditions are zero. That is generally not the case, because all the system parameters, they are having initial condition 0. That is not the case. Many a times capacitor, inductor can have some initial charge stored in it already. Okay, but if we are doing the transfer function based system modeling, we cannot consider that. That is the biggest limitation of transfer function based system. Second thing, it can be applied only for linear time invariant system. But all the systems in the nature or in the world are nonlinear and time variant. But this transfer function based system can find transfer function for linear time invariant system. So this is mainly for easier processes. If the process is complex, if the process is nonlinear, then transfer function based system modeling cannot be used to model that process. So these are the two very big shortcomings of transfer function based system. And the third shortcoming is we are giving the input at the left and we are getting the output at the right. Okay, whatever is happening in between. So at every step, so there can be many internal loops. Okay, so there can be 3 4 5 loops internally. There can be forward path, a long forward path of data flow. Okay, so what is forward path, we will see today in some numerical. So at every step, at the output of every step, intermediate step, how is the variables changing? Okay, so we don't know that in case of transfer function based system modeling. So here we are finding on the relationship between output by input. That's all. Okay, so internal intermediate step changes for the signal, how the state variables are getting propagated from input to the output, that we don't get to see in case of transfer function based system modeling. So these are some limitations. So in most of our examples, we have used a simple proportional control law realized by an amplifier. It should be understood that these conceptual designs may not be the final design to be adopted. Okay, so there can be many ways of transfer function based system modeling as well. So it may be necessary to modify a conceptual design after completing a detailed analysis of its mathematical model. In some cases, the entire conceptual design may have to be discarded as unsuitable in favor of the another design. So whenever we are finding the system model, one way we have proceeded with, we have found some kind of system model, but we find that error in that model is very high. Okay, that means we could not capture dynamics of all the system dynamics very properly. So we might discard the method totally and we might go for some other method of system modeling. So sometimes we are doing some Laplace transform based modeling or ODE based modeling, ordinary differential equation. But we can see that if the system is modeled by using statistics, that is called a statistical modeling, that will be able to capture the system dynamics better. Okay, so in that case, whatever ODE, whatever Laplace based modeling we have done so far, it has to be discarded because that was generating quite a lot of error. Okay, so we will go for statistical system based modeling in that case. So these are the kind of things we will see some time in our life, that one way we have proceeded, we have come close to the solution, not to the exact solution, but yes, come close to the solution. But we find some other method we are using, we might get a better result. So discard whatever we have done previously. So in some cases, the entire conceptual design may have to be discarded as unsuitable in favor of another design. This chapter meets the limited objectives of deriving a mathematical model of a control system for a given conceptual design. So conceptual design can be your block diagram, whatever will be given to you, or a block diagram or a signal flow diagram, which will be given to us, and we are supposed to find out transfer function for that system. So several of examples given in this chapter will be reconsidered later for detailed analysis and design. So generalized block diagram of a feedback system. So what are the ingredients of a block diagram preparation? All those things we will see. And what are the laws LAW? What are the laws of block diagram reduction? Okay, that we will see in today's lecture. So there are some 8-10, I won't say formulas or rules, but 8-10 very simple observational things that you have to observe. If you see that, you'll understand what are the techniques or what are the basic rules for the block diagram reduction. So such a big transfer function will be given to me. There may be some 4-5 internal loops, forward path, feedback path, many feedback paths interlinked, overlapped, and all those things. We have to bring all the things together and you have to find a transfer function TS, YS by XS or CS by RS. So from big block diagram to a small transfer function, which captures all the big system model into one equation of two polynomials, numerator and denominator polynomial, in time domain S. So this is actually the job of block diagram reduction and reduced into a transfer function. So this chapter meets the limited objective of deriving a mathematical model of a control system for a given conceptual design. Several of the examples given in this chapter will be considered later for detailed analysis and design. So we have already used block diagrams to represent the input-output behavior of a linear system. So I told you it always takes linear system and finds a transfer function. It cannot take if there is any initial condition. So all the initial conditions are considered to be zero while we are finding block reduction technique. So the signal into the block represents the input, the signal out of the block represents the output. So either it is called RS as the input, CS as the output, or it is called RS as the input, YS as the output, or it is called XS as the input and YS as the output. So while the block itself stands for the transfer function of the linear system, I'll show you now. So the flow of information is unidirectional, so it always flows from input to the output. And from the output, certain time it can come back as a feedback signal. And there can be two types of feedback, positive feedback as well as negative feedback. So the output being equal to the input multiplied by the transfer function of the block, a complex system comprising of several non-loading elements is represented by the interconnection of the block diagrams for individual elements. So these blocks are connected in lines and by arrows. Okay, so this is these are the slides, 4 slides that I have made. What I'll do is I'll go now for some kind of images, okay, or some kind of this handwritten notes that I have created. Okay, so I will represent them, and with respect to those notes, I will be explaining what are the basic blocks of block reduction technique. So let me just find out. This is, I will launch this notes whatever I have done. So this is the screen that I'm sharing with you, and I will increase its size a little bit. So I'll take it to around 75%. Okay, so I think it is visible by all of you. So these are some of the rules of block reduction technique. Okay, so block reduction technique or block diagram reduction, anything you can say. This is called block reduction technique. So I'll be telling you what are the rules, basic rules of block reduction technique. So you won't have to mug it up only by looking at it. You can find out, and it's very easy. Okay, so first what we have done is we have shown there is an input RS and it is passing through a system uh, which is having a GS. So I'm in the A part. So there's the A rule. So whatever system is there, so there's a system. So that this system GS can be controller, and the system can be controller and process and actuator, all these things together. So their internal transfer functions are multiplied together, and it is actually GS. So RS is given to the GS, and we are getting what is called as YS. So in that case, YS by RS, that is the transfer function, and YS by RS will be equal to GS. In this case, it is not written, but you have to understand that because RS is passing through GS and producing YS. So what is YS equation? YS is equal to GS into RS. Then I have done YS by RS, so that will be equal to GS. So in this case, transfer function is given by TS. So TS is equal to YS by RS, and that should be equal to GS. In the next case, it is given. So in the next case, you are finding that uh, two blocks, that is the controller G1S and plant G2S. So these two things are in cascade. So this is called series, but actually technical term it is called as cascade. So RS input is given to G1S, and RS into G1S is being given to G2S and YS. So what is YS equal to? YS equal to G1S into G2S into RS. So in that case, if you are finding output by input, that is YS by RS, you'll be finding that is equal to G1 into G2. So sometimes we might skip the thing S because it is understood everything is in the Laplace domain. So it is YS by RS, that is equal to TS. T stands for transfer function in S domain. So TS is YS by RS equal to G1S into G2S. Then here, whatever thing we have shown, it is called as a SP, that is the summing point. So there can be many input output ports. So in this first case, there are the two input ports. So RS, there is the command input coming. BS, it is the feedback coming. Now it is positive feedback or negative feedback, or there is another input. Either you can call it another input or feedback, whatever. And if we take feedback, so it is coming from the output of the system, then we can see that there is a positive feedback. Okay, with so positive feedback because this arrow is connected to this positive here. So what is ES? ES is RS plus BS. So RS is the command input, BS is the feedback signal. So ES is equal to RS plus BS. And what here, the same thing, BS is coming, but BS is negative. So whether it should be positive feedback, whether it is negative feedback, that is in our hand. We have to select, we have to decide. But depending on the situation, depending on the system that we are designing, okay, it is in our hand. So it will be given to you. That is, the system is coming back. Sorry, signal is coming back, and signal is having a positive feedback or negative feedback or whatever. So in this case, it is negative feedback. So RS minus BS. So error signal is equal to RS minus BS. Now this is a proof. Okay, this proof we have done last day, but again we will be doing today. What we are doing is there is a closed loop system, and we have to find out what is the transfer function. So input is RS, output is CS, feedback gain. Okay, so there is a sensor, there can be an amplifier, feedback gain is given by HS, and BS is the feedback signal. So we know that BS equal to CS into HS. So BS is given, again it is taken back and compared with the set point. So set point is RS. So this BS is actually challenging the RS. So if the output is equal to the set point, then this BS will be equal to RS. Okay. So we know that BS equal to CS into HS. This we know. BS equal to CS into HS because CS signal is taken from output multiplied with HS, and CS into HS is actually producing what is called as BS. Okay, and as this is negative feedback, so ES will be equal to RS minus BS. This thing, first line, ES equal to error signal, that is equal to set point minus feedback signal. And now BS can be substituted as CS and HS multiplied. So ES equal to RS, that is the set point, minus feedback signal multiplied by output. So what is error signal? Error signal is set point minus, this is called as feedback amplification gain, HS, multiplied by CS. The CS is nothing but the output. So this whole proof is having two parts. So there is a feedback path wise, we have explained what is the process. So ES we have found as RS minus HS into CS. Now this is called as feedback path, whereas this is called as the forward path. So from forward path we know that output is equal to GS into ES, because ES signal is coming, getting multiplied with forward path gain GS. It is given here, forward path gain GS. So H is called as feedback gain, GS is called as forward path gain, ES is called as error signal. They all are continuous time signals. That's what, when you have taken all the system into Laplace domain, everything is becoming S, GS, HS, ES, BS, CS, RS, all. So this proof, that is, if this is the system, what is CS by RS? What is the transfer function of the system? To know that, we have to assume either positive feedback or negative feedback. So in this case, we have assumed the feedback to be negative. So in the first, so this proof is having two steps. First step is find the equation of ES. So ES we have found as RS minus Y minus, because negative feedback. ES is equal to RS minus HS into CS. In the second part of the proof, you write down the equation of CS from the forward path gain. So CS equal to GS into HS. GS into ES. So error signal is coming, getting multiplied with forward gain, giving me the output CS. So CS is equal to ES into GS. Now whatever ES you have found from previous stage, substitute here. So CS equal to GS into RS minus HSGS. Now open the bracket. So CS becomes equal to RSGS, which is called as part A, minus GS into CS into ES. So CS equal to GS, substitute the value of E. Okay, you have substituted E from the previous stage, RS minus HSCS, and then open the bracket. So CS becomes equal to RSGS minus, see that in this part B, again there is a component of CS. So what is the next step? What we will do is this B part, okay, shift it to the left hand side of the equation. So CS plus, because this is minus, Y minus because negative feedback. So CS, this minus goes to the left side and becomes plus. CS plus GS CSHS equal to RSGS. So that is the next step. We can find in the next page, that is CS plus CS into GS into HS equal to RS plus GS. Now from here take CS common. What we find is 1 plus GSHS. That is the next step. CS common le lo, 1 plus GSHS now is equal to RS into GS. Now RS is the input, CS is the output. So CS by RS is output input, that is transfer function, is equal to GS by 1 plus GSHS. Very important thing. And throughout this second chapter or second module of our syllabus, always, because most of the systems are with negative feedback only, always we'll be finding out what is G by 1 plus GH. So either you can say GS by 1 plus GSHS, or you can say G by 1 plus GH. And most important thing is, if the feedback is negative, then this symbol is coming to be positive. And whenever we are going to use positive feedback, you will find that the transfer function is G divided by 1 minus GH. So that proof also we will do shortly. But before that, this is the transfer function of a system with G as forward path gain, H as feedback path gain, and G by 1 plus GH is the transfer function of the overall system. So G is the gain of the open loop system, and G by 1 plus GH is the transfer function of the closed loop system or gain of the closed loop system. So G in open loop is getting converted to G by 1 plus GH in closed loop. Now let us have a numerical and let us see what is the significance of this transfer function based gain on stability. So this is a negative feedback system, and G is converted to G by 1 plus GH. How is the gain of the system changing? So with respect to some quantities, with respect to some values, we will see how is the gain changing from open loop to closed loop. So this is called a CLTF. So whatever you have found here, CS by RS or TS or G by 1 plus GH, this is called closed loop transfer function, CLTF. Okay, with negative feedback. As this is negative feedback, this is 1 plus GSHS denominator. If it is positive feedback, it will be G divided by 1 minus GH. We will prove that shortly. Let's solve a numerical and let's see what is the significance of closed loop transfer function with negative feedback. So if a system is having forward path gain G as 0.3 and feedback gain H as 0.2. So forward gain G is 0.3, feedback gain H is 0.2. Find the overall system gain with negative feedback. So in that case, we can say that TS equal to G by 1 plus GH. Now G is 0.3 and 1 plus G into H. So if you multiply G into H, you'll be finding that it's 0.3 by 1.06, and overall system gain with negative feedback. So this is the gain with negative feedback becomes 0.283, and with open loop system the gain was 0.3. So GS was 0.3, but G by 1 plus GH becomes 0.283. Two inferences or two things can be looked or two things can be noted from here. So with negative feedback, the denominator gets positive sign. So it is 1 plus GSHS. That is very important. Okay, so with negative feedback, the denominator gets positive sign. Means denominator value increases. So if it was G, now it is 1 plus GH. So actually denominator value is increasing. So if denominator increases, overall TS value it reduces, because T is G by 1 plus GSHS. If 1 plus GSHS is greater than GS, that means TS value will reduce. You can find here, so in this numerical, GS value was 0.3, but G by 1 plus GH is becoming as 0.283. So by negative feedback closed loop type, what we are finding is overall system gain is reducing compared to the forward path gain. So whatever 0.3 was there forward path gain without feedback, with feedback it reduces to 0.283. What happens if gain reduces? System stability increases, though very fractionally, very small amount, but as 0.3 has become 0.283, stability of the system increases. So that is the second observation. So first observation is with negative feedback, the denominator gets a positive sign. So it is 1 plus GSHS. And as 1 plus GSHS is greater, that means denominator is becoming greater. That means overall system gain is reducing. And second observation is saying that open circuit forward gain GS is 0.3 is given in the numerical. Open circuit forward path gain is 0.3. But with negative feedback, closed loop, it reduces to 0.283. So 0.3 reduces to 0.283. As the gain reduces, it means that with negative feedback, the system stability increases. So negative feedback is actually reducing the overall gain of the system, and reduction in the gain is actually increasing the stability of the system. So negative feedback is increasing stability. If they ask you to explain it in the exam or in the interview, please take this example, and choosing the value are very important. So GS I have chosen as 0.3, HS I have chosen as 0.2. So G by 1 plus GH is 0.3 divided by 1.06. That will come down to 0.283. Argument is initially without feedback, the gain was 0.3. With feedback, closed loop negative, it has come to 0.283. So closed loop negative feedback is actually reducing the gain, it is increasing the stability. The same proof is done with HS or feedback as positive. Okay, so previous case we found that ES was equal to RS minus BS. In this case we are finding that ES equal to RS plus BS. And what is BS? BS is nothing but CS into HS. So ES is equal to RS plus CS HS. Same way CS is equal to ES into GS. Substitute ES as RS plus CSHS, and then open the bracket. So CS, that is output, is equal to, so output is equal to open loop gain, that is GS into error signal. So GS into HS. So from here, substitute the value of ES from the previous equation, open the bracket. You are finding two parts in the output. CS equal to RSGS. RS is nothing but the command input, GS is the forward path gain, plus CS into GS into HS. So CS is the output, GS is the forward path gain, HS is the feedback gain. Now this part B has to be taken to the left hand side. So what we are finding is CS जैसा था वैसे ही है. This CS part is taken to the left hand side. So minus CS GS HS equal to RS into GS. Now from this, take CS common, so it is becoming 1 minus GS HS equal to RS into GS. So from here you find CS by RS. So we are finding CS by RS equal to GS divided by 1 minus GS HS. So what we are finding is, with positive feedback, the denominator actually is reducing, because with negative feedback it was 1 plus GSHS. Now with positive feedback it becomes 1 minus GSHS. So how to remember? Whichever type of feedback you are giving, the denominator equation is opposite that. So if I am giving negative feedback, it is 1 plus GSHS. If I am giving positive feedback, it is 1 minus GSHS. And 1 minus GSHS actually is reducing the denominator value. If you are reducing the denominator value, means overall gain will increase. So overall gain increment means overall stability is reducing. So all these things we will prove by means of the same numerical. That is, forward path gain is 0.3, feedback gain is 0.2. So overall transfer function on overall gain is 0.3 divided by 1 minus 0.3 into 0.2. So previously it was 1 plus because it was negative feedback. This was 1 plus. Now it is 1 minus because it is positive feedback. So now this whole denominator becomes 0.94, numerator is 0.3, and the gain increases to 0.32. So forward path gain without feedback was 0.3. Forward path gain with feedback is 0.32. So gain has increased by feedback because it is positive feedback, and as gain has increased, the system stability will reduce. So there are 2 points to be noted. With the positive feedback, the denominator gets negative sign, and hence the overall denominator value reduces. It increases the overall gain. So denominator reduces means numerator by denominator increases. So overall gain means the same thing, that is TS, that is G divided by 1 minus GH. So TS value increases. If TS value increases, so open loop gain increases to 0.32. So open loop gain of 0.3, it increases up to 0.32. So with a positive feedback. Hence, the stability of the system reduces with positive feedback. So two things in comparison, we can say that whenever it is negative feedback, the overall gain reduces. Whenever it is positive feedback, the overall gain increases. So in case of negative feedback, whenever the gain reduces, it increases the stability. And in positive feedback, whenever the gain increases, it actually reduces the system stability. So this is the comparison between open loop system and closed loop system. So we have done that. And in closed loop system also, positive feedback and negative feedback. So that difference you should know. Now we are going for some basic rules of signal flow graph. So whatever time we are having, we can do only one of such gain. What is that thing called? So this is suppose a system given to you. So 2 is the input. So in book of any book like Gopal and all, so they have explained this process by means of a x1, x2, x3 and all those things they have written. So they have taken 2 inputs, x1 and x2, and they are actually getting mixed and producing the output. And then if I'm doing some change, doing some shift, then how does it affect the circuit output and how to bring it back to the present form? So I'll explain. So here, this is the forward gain. It is called as gain block. It is having gain of 3. Okay, actually it will be called as a G. And this is a summing point. What is a summing point? Summing point is where signals from different directions are coming and getting mixed. Okay, so there are 2 inputs. There is an input 1, which is the value of 2, and this is input 2. This might be the value of 1. So it doesn't matter. You can take any value. The rule will stay. So we are actually going to develop a rule. So here what's happening is, first the input is coming, getting multiplied with the gain. So it is 2, it is 3. So here the signal is 2 into 3 is equal to 6. and here 1 is coming with negative feedback. So summing point, the 6 and 1, they are getting mixed. But this 1 is not 1, this 1 is actually -1 because this is getting subtracted. So this is 2 into 3, 6, -1 is equal to 5. So the output is actually 5 for whatever system is given. So 2 is coming as the input, 3 is the gain block GB, okay, multiplied. So here the signal is 6. It is passed through SP. SP is the summing point. Summing point is having another input, that is -1. That is actually input is 1, but in negative feedback form. So this is RS into GS multiplied minus XBS. So that kind of thing we are finding. So the 6 minus 1 is equal to 5. Now, when we will be doing block reduction technique, we have to swap this kind of thing. So what we have to do is we have to shift SP, that is the summing point, to the left side of the GB. Okay, or we are going to shift this GB to the right side of SP. Both are same thing. It is written here, shifting the gain block after the summing point or shifting the summing point before the gain block. So diagram looks like this. Okay, so actual circuit is this, or system is this, output is 5. Now what we are doing is we are shifting the gain block after the summing point. Okay, now and no more change we are doing, but the output should be 5. That is constant. This shifting and all this thing should not change the output. So input should be 2, input should be 1, these are the two inputs, and output should be 5. In between whatever system configuration you can do any change, but with this 2 input and 1 input, output should be 5. Okay, but in this case just we have done the change, we have not done any adjustment afterwards. See what we can get. So previously one input was getting multiplied with a gain, and this input was not getting multiplied with any gain. This input was directly coming to the summing point. What was the actual configuration? Input 1 is multiplied with 3 and coming to the summing point, and input 2 was directly coming to the summing point with a negative sign, and we are getting output as 5. In this case, if we have shifted this gain block after the summing point, let's see what happens. So this 2 is coming to the summing point, 1 is coming with negative. So this point is 2 minus 1, so 2 minus 1 is 3. 2 minus 1 is 1, and that is getting multiplied with 3. So what is the actual output? This is 3. But we are supposed to actually get as 5. So whatever thing we have done, so if this actual circuit we just swap the position of gain block and summing point, whatever output we get is not same as the previous output. So some manipulation we have to do. So what is the main problem here? You can see that this input was getting multiplied with 3, input 1 was getting multiplied with 3, but input 2 was not getting multiplied with 3, that you can say. But in this case, whatever we have done actually, so 2 minus 1, here this 1 is also getting multiplied with 3, and this 2 is also getting multiplied with 3, but that was not the original algorithm. Original algorithm was input 1 is getting multiplied with 3, but 2 is coming directly. Okay, so some changes we have to make in this circuit or in this system, so that with this 2 input, 1 input, we are going to get output as 5 only, not 3. Okay, so what change we can make? Put a gain of 1 by 3 to the input 2. Okay, so if you are shifting this SP to the left side of gain block, in that case another change we have to do. What is that? We have to collect a gain of 1 by 3 in the second input. What is this 1 by 3? As this is the gain 3, then 1 by 3 is there. So if this gain block was equal to 5, then this was 1 by 5. This would have been 1 by 5. Okay, so whatever gain block you are shifting after the summing point, 1 upon that gain should be connected in the input number 2. So this is the rule, and if you are doing that, let's see what happens. So from here directly after shifting, we find that we are not getting the output exactly same as the input. So some changes we have to do. What change? Changes forward path, no problem. The whole forward path is no problem. This is the second input. Here we have to connect a block of 1 by 3. If you are doing that, what is it? So this is 1 into 1 by 3. So 1 by 3 comes here. The 2 comes here, and this 1 by 3 is actually negative. So this signal is 2 minus 1 by 3. Both the things are getting multiplied with 3. So it becomes 2 minus 1 by 3 into 3. That is 6 minus 1, that is equal to 5. So the top case is called as case A. Medium case, which is wrong actually, it is written here wrong system, because here in the input 2 we are supposed to put a block and we are supposed to add a gain of 1 by 3. Either we can say gain of 1 by 3, or attenuation of 3. Both the things are same thing. So in the case C, we have done that. So if you are coming from case 1, directly you have to do case C. That is, if we are shifting the summing point before the gain block, or if we are shifting the gain block after summing point, both are same thing. In that case, we are supposed to put an attenuation of the same gain, or we are supposed to put a gain of 1 by 3 in the second input. So first input will be unchanged, second input we have to control. So in that case, this 1 by 3 block extra we have to put in the second system, that is the case C. So in this case, we are finding this is the feedback will remain same. It was negative feedback. Previously also it was negative feedback. So it will be 2 minus 1 by 3 input multiplied common with 3. So this will be 6 minus 1, that will be equal to 5. So case C and case 1, they are same. So case 2 or case B is just an intermediate step that I have shown to show you what mistake actually is happening if we are not connecting this 1 by 3 block in between. Okay, so from this case B, you have come to know that somewhere something is going wrong. So just by swapping, okay, the same output cannot be obtained. So swapping, and after that insertion of a gain block with the input 2, that is to be done. Input 1 is left as it is. So this is one rule that we have done. Some more rules are there. So my handwritten notes and all these things are there. We will do that in our next lecture session. And after we have seen some 3-4 more rules in the same way. So in the book, it is actually written in one line. It is written in one line. Okay, but to show you what is the exact effect of shifting the summing point before the gain block or shifting the gain block after the summing point, what is the exact effect and how the mistake happens and how to correct the mistake. Okay, so this is a kind of a note that I have prepared to make you understand better. So exactly the same kind of notes I have prepared for other rules as well. So we will see that in the next session. Thank you.